This is session B6, the double-slit experiment, first done in 1801, but relevant to quantum mechanics. Last session, we did the decade 1914 to 1924 leading up to quantum mechanics. So we're ready to do Schrodinger's equation 1925, but we're going to explore two experiments before we do that. We've finished learning the exceptions to classical physics that led up to quantum mechanics in 1925. There are four plausible next steps that we could do. We could learn the Schrodinger equation, solve problems where we have a potential energy function of spatial coordinates and we want to know the locations of a particle in that potential. We could use this to learn about states, probability amplitudes, probabilities, measurements in quantum mechanics, etc. This is fairly typical first step in most courses and many books. The second approach, we could learn about what's called the intrinsic spin angular momentum of electrons and about spin state vectors in quantum mechanics. Learning B before A is the modern approach to learning quantum mechanics. It has some advantages but some disadvantages. It's used in some books and in some courses. We could learn the double-slit experiment classically and then quantum mechanically. Sometimes this precedes A, doing Schrodinger's equation, but parts of the double-slit experiment are difficult to explain correctly before quantum mechanics, and difficult to understand no matter when they're taught and learned. We could learn the Mach-Zehnder interferometer experiment classically and then quantum mechanically. We're going to do this order. We're going to do the double-slit experiment, the Mach-Zehnder experiment, then we're going to do Schrodinger's equation, but we're only going to do one problem, but we'll learn as much as possible from that problem. And then finally we will do spin angular momentum. This is a possible time to take a break. We need a little background on light waves in addition to what we've already covered. The intensity I of light is proportional to the square of the amplitude of the electric field. So I is proportional to magnitude of E squared. Doubling the electric field amplitude quadruples the intensity. When electromagnetic waves are present, when multiple electromagnetic waves are present, the electric field at a location in space and time adds algebraically from all the waves that are present. When there are two electromagnetic sine waves that are in phase, have the same phase, then the amplitudes add. So here we see this sine wave goes up, this sine wave goes up, and they follow exactly. They're the same frequency, wavelength, and phase. And adding them together adds the amplitude. If the two sine waves had equal amplitude, then their in-phase sum has double the amplitude, which is 4 times the intensity. Here we're going to add two sine waves that are out of phase. When this sine wave is at its positive peak, this sine wave is at its negative peak. And if they had the same amplitude, then the sum would be 0. The waves canceled each other completely. So the result of summing two sine waves depends critically on their relative phase in addition to their amplitudes or magnitudes. This is a possible time to take a break. Now we're going to look at single-slit diffraction. A plane wave of light passing through a single slit in a barrier. Now, this diagram is not to scale. The width of the slit might be small, it might be a few wavelengths of light, but it might be much larger than the wavelength of light. It might be 100 to 200 times larger. So, to the left of the barrier, we have a plane wave coming left to right of a single frequency of light, single wavelength. Where it hits the barrier, it's absorbed. Where it hits the slit in the barrier, it goes through and forms a set of cylindrical waves that start at each point in the slit. And those cylindrical waves combine in complicated fashions, but straight ahead, they are all in phase. Here are some GIFs and images from Wikipedia, different cases of single slit diffraction. And so they represent the wave in different ways. Here, the red and blue signify, positive and negative excursions of the plane wave. So it looks like a plane wave here until it hits the barrier, but where it goes through the slit, the slit is four wavelengths wide. We get a complicated pattern going through the slit where the effect is simplest straight on, where all of the wavelets get through. This diffraction is a wave phenomena. If light were classical particles, we would get sharp-edged beam due to the slit, but we don't. We get a wave. It's complicated. Here to the right is showing the actual intensity of the light that comes through. So brighter white is more intense. And we see that the maximum intensity is in the middle, straight ahead. And it falls off, and then it hits zero, and then there's a little bit of intensity in zero. And so let's see what's happening. It was a plane wave, a coherent plane wave to the left of the barrier, but once we go through the barrier, the intensity at some point on this screen here depends on the angle of that point on the screen relative to the center line of going straight through the slit. If it comes straight through the slit, we get the most intensity, which here we see as a bright white part of the blob. This red curve is a graph of the expected intensity versus position on the screen. So here we get the most intensity, and the intensity falls to zero, and then we get a little intensity, and then zero, and a little intensity again. Now, why is there a point where we get zero intensity? That point is where, if we look at how the light wave goes through the slit and gets to this point, we would see that although the wave started out all in phase going straight ahead, for this point where we have a minimum of light, or a node of light, zero electric field, light coming through the center of the slit has a half wavelength offset relative to light coming through the top of the slit at the angle where we get this minimum or node. That makes it so that all the light coming through the slit going to this angle, it always cancels. If light coming through one position in the slit gets canceled by light coming through another position in the slit. So the light waves passing through the slit at different positions on the screen interfere with one another, both constructively, adding together a bright intensity, and destructively, subtracting from one another, and at places we get zero amplitude, zero intensity, a node. This is due to having different path lengths from different positions in the slit to the point on the screen, and so different phases. And summation of the electric and magnetic fields includes the phase as well as the amplitude. The width of the high intensity blob at a distance screen, at distance L from the slit, this should say slit, it's one slit, is about twice the length times the wavelength of light divided by the slit width. So the smaller the slit width, the greater the spread on the screen. And just to reinforce, here light is not behaving like particles, classical particles. It's behaving like a wave. Here's a different simulation. Again, the highest intensity is straight ahead. And we could see that there's a node here and a node here. And another simulation. Now, what if we had two slits? Would there be one broader peak in the middle? Would there be two peaks separated by a distance? Or would there be something else? This is a possible time to take a break. Here we show a plane wave coming left to right, encountering a barrier with two slits, top slit and a bottom slit. And the light will go through and it will form cylindrical wavelets. But what will the combined pattern be on a distant screen? That drawing is not to scale. The width of the slit may be much larger than the wavelength of the light. It might be 100 to 200 times. So we're going to look now at the double-slit diffraction experiment, first done in 1801. Now, we know that Newton used a prism to separate sunlight into colors, and he could use a second prism to recombine them back into white light. Newton observed that if he formed a pencil beam of light, that beam did not spread out very much. And Newton believed that light consisted of corpuscles, what we would call particles. Now, Newton knew that if you put a knife edge into the beam, it would show waves as a result of the knife edge. Newton's contemporaries, Robert Hooke and Christian Huygens, believed that this showed that light was waves. But Newton still believed that light consisted of particles. And Newton's beliefs in optics continued to be taught in England throughout the 1700s. Until Thomas Young did an experiment in 1801. Thomas Young was an English medical physician, a scientist, and a polymath. He knew a lot about many things. In fact, a 2006 biography called him the last man who knew everything. That everything that was known in England in his time, Thomas Young pretty much knew. An amazing achievement. No one can do that anymore with the state of knowledge today. But apparently you could know enough in 1801 that someone could think that you knew everything. Now, if you have a mechanical or a mechanical engineering background, this Thomas Young is the same Young for whom we name Young's modulus, stiffness of materials. This is a possible time to take a break. Now, Young did an experiment with two slits that we called the double-slit experiment or Young's interference experiment, and this will establish the wave theory of light, overruling Newton's view. When Young passed collimated light through two slits, A and B, he found that the light that went through each slit formed cylindrical wavefronts, wavelengths, and when he looked at the pattern of the combined wavefronts, he saw that there were places where there was light intensity and places where the light was dark. And in his view, this made it clear that light was waves. Now here's an actual photograph of the pattern on a distance screen from two slits using white light. In the center we get the most intensity, and then we get a node, and then we get lesser intensity and another node. But also, red light has a different pattern than blue light because it has a different wavelength. We know that red light has a smaller wavelength, and so the angle at which we would get a node, the angle is larger for red light than blue light. Here's an example of a single slit pattern and a double slit pattern with laser light. So with the single slit pattern, we get one high intensity blob, a node, a much less intensity blob, and so forth. But when we have a double slit pattern with the same slit size but a spacing between two slits, we get this node we still see here, and this node we still see here, but the center blob now has nodes of its own, and the intensity here is more intense than here. So the wave nature of light interacting with the double slit takes some of the light intensity that would have been at a node and moves it to a location where the light is peaked. So the peaks are brighter than they are in the single slit case, and the big blob is divided up with multiple nodes within it. So the light waves passing through the two slits interfere with one another, both constructively, adding so we get a brighter intensity, and destructively, subtracting so we get less intensity or zero intensity. due to having different path lengths and phases from the two slits, in addition to the waves from within each slit interfering with one another. The spacing of the interference fringes at a distance screen, at distance L from the slits, is about length L times the wavelength of light divided by the slit spacing. The slit spacing is larger than the slit spacing, so the interference fringe spacing is smaller than the blob's size for a single slit. Now, we could go through the classical math to show how we get this formula, but it's not going to be relevant to the quantum mechanics that we want to get to. So the number of interference periods within the high-intensity blob at a distance screen at distance L from the slits is about the ratio of the two quantities we had. 2 times the slit spacing divided by the slit width. Physicists were able to successfully explain the double-slit diffraction interference using classical electromagnetics and optics. But what about Einstein's photons? Please pause here and think about what the experimental result would be if we reduce the light intensity enough that only one photon is going through the experiment at a time. Does a photon split into 2 photons, one for each slit? Does the interference pattern disappear because light is photons, not waves? Does each photon go through both slits somehow? This is a possible time to take a break. Now, an experiment was done in 1909 to greatly reduce the light intensity. And with modern lasers, it's possible to reduce the intensity so that a single photon goes through the experiment at a time. Concerning wave-particle duality for photons, Einstein wrote, "It seems as though we must use sometimes the one theory and sometimes the other, while at times we may use either. We're faced with a new kind of difficulty. We have 2 contradictory pictures of reality. Separately, neither of them fully explains the phenomena of light, but together they do." Now, what we're going to see is that an individual photon could be detected almost anywhere on the detector screen. The hits of prior photons give us no information about where the next photon will hit. If we record all the spots, all the hits, the pattern will better and better match the classical intensity pattern as more and more photons hit the screen. The probability for where the photons hit the screen matches the classical intensity pattern. We'll see this when a large enough ensemble of photons independently hit the screen. Diffraction experiments and other double path experiments can also be done with electrons, atoms, etc. Following is an image of the double-slit diffraction of electrons, not photons. This first image shows where the electrons hit the screen, when 11 electrons have hit. Now this is rotated 90 degrees relative to the examples I gave in the past. So what previously I showed vertically is going to show horizontally here. But in frame A with 11 electrons, we see no pattern that we can recognize. Frame B has 200 electron hits. And it looks like they could hit pretty much anywhere. We don't see any clear pattern. Frame C has 6,000 electrons. Now you could look at this and come to two conclusions. You could say, well, that electron can hit anywhere. I mean, look, it could be anywhere. When we have enough electrons, it's just going to be a screen of white. Or you could say, well, yeah, okay, but it's kind of a black thingy here and a black thingy here, and I don't know, maybe a black thing here and a black thing here, but I don't know. Let's look at frame D. Frame D has 40,000 electrons. And maybe we'd say, well, gee, okay, it's kind of brighter here than it is here, and brighter here, and darker here, and brighter here, and darker here, and brighter here, and darker here, and brighter here. Frame E has 140,000 electrons. It's definitely brighter here. It's definitely darker here, but we don't see a solid black line here, but it's brighter, darker, brighter, darker. Definitely some kind of probability thing. This is a possible time to take a break. Let's see how quantum mechanics describes one photon traveling through one slit. So we're back to one slit now. Photons and one slits. One slit, one photon going through it. The photon does go through it. The photon does hit the screen. It hits the screen somewhere. We record it. We let another photon go through. We record it. One at a time, we let photons go through. We record it. And after we've let hundreds of thousands of photons go through one at a time and looked at the recording, we see the particle's probability density for where it hits the screen. Looks kind of like this for one slit. Now for quantum mechanics, we will say that the particle has a wave function, also called a probability amplitude, for where it hits the screen. We'll use y as the direction of the screen, and here we're using vertical. So the wave function for a single photon going through slit 1, hitting location y, the wave function will be Greek capital letter psi sub 1 of y. It turns out that the particle's probability density for where it hits the screen is not psi, but the magnitude of psi 1 squared. That is the probability density. We will come to understand that more over time. For now, I just tell you that quantum mechanics has to distinguish between a wave function and a probability density. Now for a single slit, the intensity is highest straight on, and then there's a node, and then another one. And I've sized this differently than that earlier drawing where this was more spread out vertically. But don't let that confuse you. I'm just trying to show you here what the probability density function looks like. So not to scale with the previous drawings. This is a possible time to take a break. For a photon or any particle, an electron, that definitely passed through slit 1 and it hit the detector screen, the particle's wave function where it hits the screen is psi sub 1 of y. And the wave function can take on values that are complex numbers. The particle's probability density for a particle hits at the screen at location y will be rho sub 1 of y, which will be the square of the magnitude of the wave function. The photon did hit the screen, so the sum or the integral of the probability density over the whole screen will be 1, because that's 100% probability, and every particle did hit the screen. Every particle that went through the slit hit the screen. The wave function is also referred to as probability amplitude. It can be confusing at first. There's a probability amplitude and a probability density or probability. Those are two separate things. They're related. You can compute probability density from probability amplitude, but they're not the same, and you must not use a probability amplitude in a place where you should have used a probability density. The wave function or probability amplitude it's generally a function whose values are complex numbers. Since psi may be a complex number, we used magnitude squared for probability density rho, not simply psi squared. Wave functions use complex numbers. You don't have to know complex numbers to get a lot out of the remaining videos. However, we will use complex numbers so the material is correct. The second video after this one will be on complex numbers, but you don't have to understand complex numbers to continue this video series. The screen could also be replaced with a set of detectors, electronic detectors. For the separate case of only having a slit 2 in a different location than slit 1, for a particle that definitely passed through slit 2 and hit the detector screen, the particle's wave function where it hits the screen will be psi sub 2 of y, and the probability density will be rho sub 2 of y, and that photon did hit the screen, so the integral of rho sub 2 over the screen will be 1, or 100%. Rho sub 2 has an identical shape to rho sub 1, just displaced in y because the two slits are displaced. This is a possible time to take a break. When we have two slits equidistant from the source, and we take no step to measure which slit a photon passes through, then for a photon that hits the detector, that photon's wave function where it hits the screen is psi of y is the sum of psi sub 1 due to slit 1 and plus psi sub 2, the wave function due to passing through slit 2, that sum divided by square root of 2, which we'll explain in a bit. These values could be complex numbers, and the particle's probability density at the screen is rho of y is the square of the magnitude of psi. The photon did hit the screen, so the integral of rho of y over the screen will be 1. 2 slits, 1 photon. Slit 1, slit 2. Detector screen, we'll call y the vertical axis here. The particle's wave function where it hits the screen. Psi of y is psi sub 1 of y due to slit 1 plus psi sub 2 of y due to slit 2 divided by square root of 2. Here, this black arrow I'm showing where just 1 photon may be hit. But this complicated red curve here is the actual photon probability density for where it will hit the screen. Probability density rho of y is the square of the magnitude of this psi. Now, notice that we do have sort of a central blob and a node and a little blob and a node, except now within each blob there are additional nodes. So the amplitude is highest right between the slits, the center line between the slits. But then a little distance away we get a node, and then a lesser peak, and a node, and a lesser peak, and a node, and a lesser peak, and a node. We get this pattern because of the 2 slits. The 2 slits were equidistant from the source of the photons, and each photon could have traversed either slit with equal likelihood. So the wave function for the photon that hits the screen is the sum of the wave function for a photon known to have traversed slit 1 and the wave function for a photon known to have traversed slit 2, which we worked out earlier, divided by square root of 2 to normalize the total probability for hitting the screen to be 1. For the case of double-slit diffraction, summing the 2 single-slit wave functions results in interference, constructive and destructive, in the resulting probability distribution. This is due to the relative phases of the 2 single-slit wave functions at some position y on the screen. A given position y has different angles to the 2 slits. The 2 wave functions might have the same sign at that position and reinforce constructively, or they might have opposite signs and interfere destructively. If they have equal magnitude and opposite signs at some point on the screen, they will sum to 0 at that point, and there will be a node there for the double-slit photon's wave function. This is a possible time to take a break. With this quantum mechanical wave function for the photon, interference is due to each photon interfering with itself, due to the 2 slits, not due to a photon interfering with other photons. We can do the experiment with photons going through the experiment one at a time, and we will build up the probability distribution. So we see the same probability distribution by accumulating individual photons slowly As for the intensity of a classical light beam of electromagnetic fields, electromagnetic wave, we can think about this in one of two ways. We could think that each photon is conveying the phase information that's present for the classical light beam sine waves of electric and magnetic fields, or that the classical light beam and electromagnetic waves, they have their phase behavior, they get their phase behavior as a result of the ensemble of a huge number of individual photons. Recall that probability density rho was the square of the magnitude of wave function psi, and also that the classical intensity of light is proportional to the square of the amplitude of the electric field. So the intensity I of light is analogous to the probability density rho being built up from the ensemble of photons. Einstein said that classical continuous electromagnetic waves of Maxwell's equations are only time-averaged values averaging over very large numbers of photons. The wave function psi seems to have a somewhat similar role to the electric field amplitude and phase as far as probability density rho and light intensity I are, built from them, but that's as far as we can say. The double-slit diffraction experiment and other diffraction experiments have also been done with electrons, atoms, and molecules. The detection of the particle hits is observed to be inherently probabilistic, unlike classical mechanics. In place of the photon wavelength, the diffraction pattern depends on the de Broglie wavelength, which we covered earlier, Planck's constant divided by the particle momentum of the particle, for particles with mass, like electrons and atoms. Superposition of the two single-slit wave functions results in interference, constructive and destructive, in the resulting probability distribution. The diffraction pattern is due to the particle's superposition wave function. Interference is due to each particle's wave function interfering with itself, due to the two slits or a crystal, depending on the experiment, not due to interference between particles. We could send particles through one at a time. We could send atoms or molecules through the experiment one at a time, and an atom will interfere with itself, a molecule will interfere with itself, and produce the probability distribution. The interference of sizable molecules with 810 atoms and 10,123 atomic mass units has been observed. Physicists continue to do diffraction experiments with larger molecules to see how large an object still shows quantum diffraction interference. Now pause the video and think about any possible objections you have to the material presented in this video, and then I will talk about some objections. This is a possible time to take a break. Here are some possible objections you might have. What is the wave function really? Is it like a water wave? Is it like a light wave? No, it's different, and it's hard to explain. We will get more experience in coming lectures by looking at some real wave functions and seeing how they come about and how they behave. It's hard to explain in a few words what is the wave function really. Does a photon really interfere with itself? How can this be? If we send a molecule through two slits, how can it interfere with itself? The answer is partial. Whether for a photon or a particle with mass, when a state is the superposition of two or more wave functions, interference, constructive and destructive, can and does occur. But as to how this can be, we will get more experience in coming lectures. The photon travels at the speed of light. Can we really use quantum mechanics here? Well, we can't use non-relativistic Schrödinger's equations for the path of a photon that travels at the speed of light, but there is superposition and interference in relativistic quantum mechanics as well, and the results that I'm presenting here are true. Is each photon traveling through both slits? How can this be? That is an excellent question and a disturbing question. The remainder of this lecture will talk about that. This is a possible time to take a break. Quantum mechanics says, quantum mechanical phenomena are fundamentally probabilistic in nature. The wave function is the probability amplitude for the particle, and the square of its magnitude is the probability density. The wave function is not a displacement in a medium, such as a water wave or other classical wave like a sound wave, but it's not like electric fields in a vacuum either. So we need to build up some experience about what a wave function is. When a particle can take multiple paths or trajectories within a system or experiment, the particle's wave function or probability amplitude is a superposition or linear combination of the wave functions that would obtain for each possible definite path. And the probability density is the square of the magnitude of that superposition wave function. Differences in phases in the superposition give rise to interference, as we see in the probability density. It's wrong to say that an individual particle took all possible paths. It would be better to say that the wave function is as if the particle could take any possible path with some probability amplitude, and we don't know which path it did take. We cannot predict where an individual particle will hit the screen. We can only predict the probability density. Richard Feynman called this a phenomenon which is impossible to explain in any classical way, and which has in it the heart of quantum mechanics. In reality, it contains the only mystery of quantum mechanics. Much of quantum mechanics can be understood by carefully thinking through the implications of this experiment. However, our perspective on this experiment improves as we learn more quantum mechanics. It's fine to be dubious in your first exposure. In fact, you will still be dubious a year later. The more experience you get with quantum mechanics, the more you can come to believe that it's a true reflection of reality. But it's still hard to understand how it can be or why it is. In particle physics, multiple or many interactions are possible. The wave function for the particle is the sum or superposition of wave functions for all possible interactions that can occur, weighted by their probability amplitudes. An unstable nucleus might have two possible decays with different probabilities that contribute to its decay half-life. An unstable particle might have multiple possible decays. Collision of two high-energy particles in a particle collider could create many different particle pairs. All possibilities contribute to the superposition wave function for the system. This is a possible time to take a break. If we didn't measure some aspect or attribute, such as which slit the particle traversed, then we don't know it. End of story. And we should not make a guess about it. We should not try to apply human macroscopic world experience, reason, and logic, or classical understanding to a quantum world measurable quantity that we did not measure. The fact that the probability distribution shows interference due to the wave function being a superposition due to the two slits, as if a single particle could possibly go through both slits, is very confusing for us lay people, amateurs, to understand and believe, because we don't see anything like this in the real macroscopic world that we see and model from the time we're infants. It's different than the entirety of experience, reason, and logic about solid objects that our brain comes to understand from a lifetime of living. Though we do see how water waves pass through slits, but all quantum experiments verify quantum reality, and we can come to believe it, but it's difficult to believe it at first and even after a while. In general, when we do a measurement of a quantum system, the state of the system changes or randomizes after the measurement, except for a special case that we will talk about later, that we're not going to talk about now, about eigenstates and energy eigenstates. For double-slit diffraction, if we attempt to measure whether the photon or electron definitely traverses slit 1, slit 2, or both slits, the which path measurement changes the system and the probability distribution. For this change system, we will get the single slit result for slit 1 when the particle was detected, transiting slit 1. If the particle was detected transiting slit 2, we will get the single slit result for slit 2. We no longer get the double slit interference. Measuring which path changed the experiment. This has been verified experimentally. This is true even if we add instrumentation to measure which path, but we don't look at the result of which slit got traversed. just adding the instrumentation or the mechanism to either slit, doesn't even have to be added to both slits, it changes the system and the results. So we can't take a sneak peek and draw a conclusion. When we see the double slit diffraction probability distribution, we just don't know which slit the particle went through. Detecting a photon removes and destroys that photon. So we can't detect it and reproduce it. In destroying it, we destroyed some information. The detector screen constitutes a measurement of position, but not of which slit got traversed. Well, gee, quantum mechanics is confusing and mysterious. But don't give up. With more experience, the confusion and the mystery will reduce a little. But it'll never completely go away. No class can promise you that after that class, the confusion and mystery will be gone. It won't be. You will hopefully get progressively more comfortable. This is a possible time to take a break. If you want to read about alternate interpretations of the experiment that we will not cover, you can go to this link on Wikipedia. However, I caution you, in general, the multiple interpretations, there are no experiments that have been found that determine that one interpretation is correct and the others are incorrect. So they are more or less, equally true, or at the moment undecidable between them. Maybe later experiments will be discovered that rule out some interpretation, or that prove that one interpretation is correct or more correct than the other. But scientists have been looking at those interpretations for 40 or 50 years, and so far not ruled them out. We are not going to cover the different interpretations, so if that's where your interest lies, you can look at that Wikipedia page. You can find videos that go right to discussing those interpretations. But the thing is, without more quantum mechanics background, you're at the mercy of believing, whatever lecturer is on the video. You can find one lecturer persuasive and another not persuasive. But that's not really a quantum mechanical understanding. That's just believing a person that's talking to you. Our next lecture, B7, it's a different double path experiment that has also been done with photons and, in this case, neutrons. It's a different setup, but it has the same kind of impact in helping us to understand that quantum mechanics is different than classical mechanics. This is the end of lecture B6.